So good afternoon, everyone. Welcome back to Math 122. Today we're going to push forward with integration. Before we do that, though, how was the exam? Okay? Or felt it was hard? Any thoughts at all? Yeah.
The critical points question was the one that troubled me the most, because when we did it in class, we just did it like factoring polynomials, and then when we got to that, I did not know how to do that.
Yeah, that one I stared at for a good moment. I was trying to figure out how to factor that. Couldn't tell if my brain died or
This was
actually difficult.
I didn't know how to factor e to the
with the one with the product rule with e to the minus 2x.
I think I tried the product, but I didn't know what to do to factor it after that to get back some time sums.
There's like a little, I was like super confident about, and then I opened it and I was like,
Yeah.
what?
Okay.
Yeah, that's the only one that really threw me.
Any other comments on the exam? We feel it was probably a little bit harder than the first exam, but nothing that you hadn't seen on the homeworks. I haven't graded it yet. I'm gonna do that this weekend. I just had this week was not gonna be possible for me to start grading until basically tonight. So I'm gonna start tonight, and I'll grade through the weekend, and hopefully get them back to you all on Tuesday of next week. So we're kind of close to the end of the semester. We only have like 3 classes left, and I'm trying to think, is one of those days supposed to be a review? Oh wait, no, we have 4 classes. Or no. 3 days left, including today, right? Okay, so we're gonna do a little bit of chapter 6. We're probably gonna do, I don't know. We probably will go up to like 6.4, I think is what we're going to do. So what I'm going to post on the Wiley is like one final homework assignment that's going to include all of the problems from this part of the class, which are viable to be chosen for the final exam. And I'm going to have to take a look at the dates of when I can make things due, because I know there's some restrictions on when I can make things due when it's getting close to finals. So I'll just make sure to abide by all of that. So if I can't get the assignment in before then it'll be like optional or something like that. So regarding the final, it's going to be in our usual classroom, May 2nd, 4 p.m. Jacob, are you going to do a session before that?
I won't. My SI ends the last day of class, but there'll be other SI people doing just general math 122 final exam review.
Okay.
In the ballroom at Russell House, I think.
Okay, so can you post an announcement with the details about that at some point? Okay, thank you. So. Okay, yeah, so that's where we're at. So are there any administrative questions, comments, or concerns before we start in on content? Yeah.
The final is cumulative, right?
Yeah, final is cumulative. So our exams in class have been, 4 pages or something like that? So the final will probably be 6 pages, and you'll have 2 hours. It'll be more time than you would have in class, basically. So there'll be more stuff, but there'll be more additional time than there is additional stuff. So you should have even more time, basically, per problem. And yes, it will cover everything from chapter 1 up to chapter 6. There's not going to be a recency bias towards the stuff from the end of the class. But I'll tell you in advance how many questions are going to come from the integration stuff that we do between exam 2 and the final. Does that answer your question? Any other questions? Yeah.
So the
Yes.
But
So,
you still have to take the final even if.
correct. So the idea is like if exam 1 you made a 50%, and then exam 2 you got a 75%, and then on the final you got a 73%. Then the way that your grade will actually turn out, I will count exam 1 as a 73%, and I will count exam 2 as a 75, and the final as 73. Okay, so if you do better on the final exam than you did on one of the first exams, one of the 2 midterm exams, then it'll count for your final grade, and it will also replace that low exam score.
So it's included in your final grade no matter what the final is.
Yes, so everyone needs to take the final.
Does that work in reverse?
d-
Like if you do worse on the final than you did on like a first
No,
test?
no. So the idea is just if you do the final, like the idea is that you could have done poorly on exam 1, but then got caught back up and learned the material and studied and got on top of that later on through the semester. Does that make sense? So if you then show proficiency later, okay, then I will allow you to replace one of the 2 midterm exams with your final exam score. Good question. Are there any other questions? Yeah.
Don't you drop like 2 of the lowest homeworks?
Yeah, I'll drop the 2 lowest homeworks and the 2 lowest quizzes. All right, if no other questions, then let's start. So I wrote that we're going to do 5.4, 5.5, 5.6, and 6.2 today. Really, the main thing that I want to talk about is 6.2, and we're going to kind of breeze through these 3 sections right at the start. So to that end, let's remind ourselves what we're trying to do with all of this integration business. What we're trying to do is find the area under a curve, right? And the area under a curve has a physical meaning if the function describes something physical like velocity or a rate of change of some kind, then the area under the curve will have a meaning in this word problem or whatever you might have, right? So we can find the area under the curve easily if it's made up of just shapes that we already know how to find the area of, like squares or rectangles or triangles. But if the area under the curve is weird looking, then we have to resort to what we call Riemann sums. So Riemann sums are where we approximate the area by these rectangles, and the more and more and more of them we use, the better and better and better the approximation will be. Sorry, I just have to scroll to the right spot. And then we define what the integral is, right? We define that the integral from a to b, which we use this weird looking s, and then a and b to say where we're going to start and stop counting area, respectively. And then we have f of x, which is the function, and then dx, meaning that we're integrating with respect to x. So the integral was taken to be the limit of the Riemann sums, where the number of rectangles became infinite, okay? So it turns out that, well, actually we define, when we write this, okay, when we write this right here, we're talking about this orange area here, the true area under the curve, not an approximation, but what is the actual area, okay? So that was what an integral is. And so far, we have no way of actually computing integrals except possibly by using a computer to do it for us or by approximating the area using Riemann sums, okay? But today we're going to learn how to actually do it and figure out what that area is, okay? So that's the goal for today. But before we do that, let me talk about, we also learned about integrals as area, and we always talk about, well, it's the area under the curve. Well, what if the function is beneath the x-axis? Well, then we take the integral to be whatever is the negative, okay, of that area. So area which is above the curve, we count in a positive way, an area which is beneath the beneath the x-axis is counted in a negative way. Okay, so we had this example here where we tried to do all of these integrals where we're going to count this as positive area, the 0.75 as negative area, the 2 as positive area, and the 1 as negative area. Okay, so altogether, the integral from 0 to 5 for this one would be 2.5 minus 0.75 plus 2 minus 1. Okay? Which would be what? 2.5 minus 0.75 is 1.75, and then we add 1, so it's like 2.75. We agree with that? I think we do. Okay, so that would be how we do that one. Any questions on what we've learned up to now regarding integration? Or Riemann sums? Okay, sweet. Then, we also learned about the area between two functions. Well, we take the area between two functions to be the integral of their difference. Okay, the integral of their difference, because the integral of their difference is what we get when we just take the area under the area under F, so that's this area shown in red, and we take away the area which is under G, which would be this area here. If we take away this area from the larger one, then we will end up with the orange area, right? So that's integration for finding the area between two functions. But again, we still haven't learned how to actually do integrals, which is what I want to talk about today. But before we do that, I want to talk really quickly about a couple different things. First of all, what are the units? Okay, what are the units? So the units of the integral from a to b of f of x dx are the units of f of x multiplied by the units of x. So, for example, the integral from 0 to 5 of v of t dt. So v of t is measured in miles per hour, for example, and t is measured in hours. Then the units of the integral from 0 to 5 of v of t dt would be miles per hour times hours. We cancel, and we end up with just miles. Okay? So we take the units of f and multiply with the units of x. Okay, that makes sense, because we're doing an area here, right? What we're really doing is multiplying like height times width. The width is measured in x, and the height is measured in f of x. So we multiply those two things together to get the units of the integral. Okay? So that's the units. Any questions on units? Okay. Then I'm going to skip a lot of this, and we're going to go to, oh my god, the fundamental theorem of calculus. We're finally here. So this was what it was all about, I guess. Well, I don't know if I'd say that this is what calculus is all about, but this is the biggest theorem in calculus, which is why they call it the fundamental theorem of calculus. And here's what it says. The integral from a to b of the derivative of a function is equal to the function evaluated at b, actually let me, function evaluated at b minus the function evaluated at a. And one notation that I'm going to introduce for that is this. We do f of x and we do a bar on the right-hand side, and we put b at the top and a at the bottom. So this colon, this symbol here means this is a notational definition. Just means that I'm telling you that when I write f of x with this bar on the right-hand side and b and a, what I mean is this. So plug in b and then subtract, plug in a. Okay, so this is the fundamental theorem of calculus. So what does it really say? Well, it tells you that now you can actually find the area under any function whose derivative or whose antiderivative you know, right? So as long as you know that a function is the derivative of another function, you can find out what is the area underneath a function's derivative. And I know that sounds like a really weird way of saying it. We're going to rephrase it in a different way a little bit later on, but let me show you an example. So for example, all through this class, you have, I think everyone would feel comfortable with the function f of x equals x squared. Its derivative is f prime of x equals 2x. So what is this saying? This is saying that you can find the integral from, say, 2 to 5 of 2x dx. Okay, the area under the function 2x from 2 to 5 is given by x squared, where we plug in b and a, which in this case b and a are 5 and 2. And that would be 25 minus 4, which would be 21. Okay, and let me just draw a picture of what this is. So the function 2x is a line with slope 2. And we start at 2, we go up to 5, and we want to count up basically what is this area between here. It turns out that you can find this area incredibly easily as long as you know that 2x is the derivative of x squared. Okay? So for any function that we would replace 2x by, as long as we know some other function such that that function's derivative is our integrand, okay, which we call this function inside the integral, we call that the integrand. Okay, as long as we can find a function whose derivative is our integrand, then all we need to do to find out what the area is plug in two numbers, right? And plugging in two numbers into a function is way easier than doing Riemann sums, right? Doing Riemann sums, we have to figure out how many rectangles, we have to figure out whether it's an under or an over estimate, and do all of this crazy shenanigans, and at the end of the day, what do we get? Just an approximation of the area under the curve. But this fundamental theorem is so powerful, it tells you you can actually find the true area simply by plugging two numbers into a special type of function. So the crux of the rest of this class is going to be when we want to do something like this, we want to figure out, well, what's the function that I should plug into in order to find the true integral? Okay? So is the goal clear? we have any questions about that so far? Okay. So there's only one other thing from, oh, well, I want to say one more thing. If f of t is a rate of change, for example, velocity is a rate of change of distance, then the integral from a to b of f of t dt represents the total change from A to B. Okay, so for example, velocity is a rate of change of distance. So if we integrate the velocity over a time period, we get the total change in distance from time A to time B, aka how far we went, right? So if f of t is measured in like milliliters per hour, or miles per hour, or meters per second, or sales per day, or something like that, okay? Then the integral will tell us, from A to B, will tell us like what was the total change in that quantity from time A to time B, okay? So you could say like from day 1 to day 7. If I know how many sales per day I'm doing, I integrate the sales per day from day 1 to day 7, I get the total sales in that 6-day period or 7-day period, whatever. Okay? All right. Finally, oh yeah, sorry. Okay, the last thing I want to talk about from chapter 5 is average value. So this is just a fact. 1 over b minus a times the integral from a to b of f of x dx is equal to the average value of the function over the interval from over the interval AB. Okay, so what do I mean? I mean, if you have A and B here, if you take this area, right? You take this area and you divide it by the width, then you're going to get the height of a rectangle whose height would be basically the average height of the function over this region. Okay, so if we took all of the points here and we averaged their height, well, the average height would be somewhere in the middle, right? And this is how we get the average value of a function over an interval, is actually we take the integral of that function from A to B and we divide by this distance here, right? We divide by this distance. Okay, so this is kind of like, you know, there's 40 students in our class. I add up all of your exam scores and divide by 40 to get the average, right? So this is essentially the same thing, except we're dealing with infinitesimals. Okay. Questions on average value? Okay, we're going to return to some of these concepts later on, but I want to get to the main one. Okay, I want to get to the main one for today, which is in chapter 6. So I'm going to section 6.2. Okay, going to section 6.2. And we're going to start with these A, B, and C really quickly, just to remind ourselves about derivatives, and see how we're going to go about undoing this process, okay? Because I've already sort of alluded to the fact that we're going to be trying to find antiderivatives of functions, okay? So let's talk about what an antiderivative is in a second after we try these derivatives. So to do the first one, I just need to use the e to the kx rule, right? The 5 hangs out, and then we have 2e to the 2x. So all told, we get 10e to the 2x. For the second one, g prime in this case is going to be 1 over 7x plus 1, and then we have to multiply times the derivative of the inside because of the chain rule. So that gives us times 7. So that would be 7 over 7x plus 1. And then finally for the last one, h prime is equal to, well, what do we have to do for this one? We could do this in two ways. We could use the quotient rule if we want, but I think a smarter way, or a faster way, not necessarily smarter, would be to do 2 times 2x minus 1 all raised to the negative 1 and use the chain rule. So then we would get the 2 is going to hang out, and then we're going to have 2x minus 1 raised to the negative 2, and we also have to multiply times negative 1. So multiply times negative 1. And then we have to multiply still by the derivative of the inside because of the chain rule. And that becomes a 2 here. So all told, what do we get? On top, it's going to be negative 4. And then on bottom, I think we have 2x minus 1 all squared. Okay. So if you think back to when we learned the chain rule, okay, when we learned the chain rule, the first thing we did was we practiced doing these sort of reverse composition functions or problems, where originally you're used to having people ask you, here's two functions, what do I get when I plug one into the other, right? And then we had to sort of reverse engineer that, where we said, I have a function, express it as a composition of two, right? So this is sort of like this reverse thinking. Same deal is going to be true for antiderivatives. So we've gotten very proficient in doing this forwards, right? Figuring out what is the derivative of something. And now we're going to ask the opposite question. We're going to say, what is the function such that 10e to the 2x is that function's derivative? Okay, that function's derivative. So we're going to reverse the process. All right, so that's what an antiderivative is. So let's write some text here. We say f of x. So oftentimes I'll use capital F to refer to an antiderivative. So capital F of x is an antiderivative of little f of x if the following is true. We just need the derivative of capital F to be equal to little f. So, for example, x squared is an antiderivative of 2x. The reason being, So this is my capital F, yes? If I take the derivative of x squared, I get 2x, which is my little f. So 2x is playing the role of little f here. X squared is playing the role of capital F. And we have this relation that the derivative of capital F is equal to little f. Are there questions on this process so far? Okay, so you can probably see where this is going. We're going to learn all the rules in reverse, right? How to go from e to the kx to what's the antiderivative of e to the kx? What's the antiderivative of 1 over x? And these sorts of things, okay? So the first one we're going to learn will be the power rule. It's basically just you reverse the power rule for the derivative, right? That's what's going on here. But there's one other thing I want to touch on, which is the language that I'm using here is weird. We say f of x is an antiderivative of f of x, not the antiderivative of f of x. So n means, or the implication of that language, right, is that there could be other functions which are also an antiderivative of 2x. Can we think of any other functions besides x squared such that this would be true? F prime of x is f of x, yeah?
X squared plus 5.
X squared plus 5 is also an antiderivative. It's also an antiderivative of 2x, because when you do the derivative of x squared plus 5, the 5 just goes away, right? The 5 just goes away. Okay, so antiderivatives are not unique. Unique's the word we use in math when we say there's only one of them. Well, same in regular English, right? So it's any function whose derivative is your integrand, for example. Okay? So that's how we do antiderivatives. So let's do some practice. Okay. So let's start with A here. So we have 30x to the 4. And we want to ask ourselves, we have three functions here. We want to determine whether any of them are antiderivatives of little f. Well, in order to check that, I know that f of x is an antiderivative if the following is true. I need f prime of x to be equal to my original function little f of x. So let's just take the derivative of each one of these and check if it's the same as the function. So if I were to do the derivative of 120x cubed, I would get 360x squared. And 360x squared is not the same as 30x to the 4, so I would say no, f of x is not an antiderivative of little f of x. Okay, let's try g. Well, let's take the derivative of g and see what we get. In this case, we would get 30x to the 4. So I would say yes, g of x is an antiderivative of 30x to the 4 because when I take its derivative, I get 30x to the 4. So it's one of the many, many functions whose derivative is f of x. Okay? So let's see the second one. The second one is going to give us an idea of... Yeah, sure. So the second one is going to give us an idea of what is going to be the antiderivative of e to the x. We already know that the derivative of e to the x is e to the x. And it turns out it's also true by that implication that the antiderivative of e to the x will also be e to the x, right? Plus any constant. So if I take f prime of x here, I get e to the x, which is not the same as 2e to the x. If I take the derivative of g, then I'm going to get 2e to the 2x, which is also not an antiderivative of this function, because in this function we just have x in the power, and in this function we have 2x in the power. So this is also a no. And the last one, if I were to take the derivative of h, even though there's that plus 1, I'm still going to get 2e to the x, and then the plus 1 is going to go away because I'm doing a derivative of a constant. And this is an antiderivative because when I take its derivative, I recover the function g, little g. So h of x is an antiderivative of g, little g. Okay? And then the last one, 4 over x. We want to find an antiderivative for 4 over x. Well, let's just try some of these. If I do this one, I get 4 times 1 over x. Right? 4 times 1 over x, which is 4 over x. So this one is an antiderivative. For g, g prime is going to be 1 over 4x times 4 plus 0. So that's chain rule there. And that gives me 1 over x. So this one is not an antiderivative. And the last one I would do by using the power rule. 2x to the minus 2. If I do its derivative, I would get 2 times negative 2 times x to the negative 3, which would be negative 4 over x cubed, which is also not the function I'm looking for. Okay, so are these examples helping to clarify where we're going here? All right. Any questions so far? All right. If not, then time to learn some antiderivative rules. Let's start with the most basic one. Actually, before I even do that, let me start with properties of integrals. The first property is that the integral of a sum is equal to the sum of the integrals. Okay, so we had a similar rule for derivatives. This is called linearity.
Is it still 6.2?
Yep. I think so. Yeah. The next rule is an extension of the first, which says that the integral from a to b of a constant times f of x is equal to the constant times the integral from a to b of f of x dx. Okay, so integrals of sums are the same as sums of integrals, just like how derivatives of sums are sums of derivatives. And same deal with the constant multiple rule. We can take it out front and just leave it alone while we take the integral of the function. And maybe one more. One more integral property, which is that the integral from b to a of f of x dx is equal to the negative of the integral from a to b of f of x dx. Yeah, sorry. Okay, so the integral from b to a. So when I say b to a, we're sort of counting in a leftward direction. We're like not accumulating change, but we are, I don't know what the reverse of accumulating is. We're removing accumulated change. Okay, so if we change the bounds, you pick up a minus sign. And then sum and difference rule. Okay, sum and difference rule, basically. Okay. So those are some properties of integrals, and now let's actually write down some rules. So the first rule is the integral of I need to talk about something else before I talk about these rules, which is this box. Sorry, I hate to jump around on you all, but I need to talk about this first. So this should say definite versus indefinite integrals. So what is a definite integral? A definite integral, in fact, why don't I make this one? We'll make that one red. Okay, so a definite integral is integral from a to b of f of x dx is a number, okay? It is the area under the curve. Okay, so here's A, here's B. We are talking about this area, right? When I talk about an indefinite integral, okay, I'm going to talk about something completely different. When I write an integral, but I don't put the a and the b, I just do the integral sign, and I put f of x dx. Then what I'm referring to is not a number, okay, is not a number. What I'm referring to is a class of functions capital F of x, okay, a class of functions capital F of x, such that f prime of x is equal to f of x. Okay, so remember how we had sets at the beginning of class, and a set was like a bucket, right? And in my bucket, I can throw in various numbers, right? Like we could have the set with the numbers 2, 4, 6, and 8 in it. And then we also had intervals where we could put in infinite numbers of numbers into our bucket, right? So that's like I can throw into my bucket all of the numbers which are bigger than 1 but smaller than 2. So now we have another bucket, but in my bucket I'm not going to put numbers, I'm going to put functions. I'm going to put in every function that satisfies this property. Every function such that if I take its derivative, I get little f. Okay, so like for 2x, we said it could be x squared, it could be x squared plus 5, it could be x squared plus 71, okay? It could be x squared plus or minus anything, right? And still be an antiderivative. So I'm going to take all the antiderivatives and throw them in a bucket. And this bucket is what I call this. The indefinite integral of f of x is the collection of all antiderivatives, okay? So for example, the integral of 2x dx, if I don't put numbers here, then I'm talking about the indefinite integral. This is the collection of functions of the form x squared plus c. Okay, so x squared plus c, where c is any constant. Okay, so when I write this, what I'm referring to is an object which is like a bucket which contains x squared. It also contains x squared plus 1. It also contains x squared minus a billion. All of those functions are in this collection of functions. Okay, so that's what I mean when I say a class of functions. I mean a collection or a set of functions. Okay. So, if there are numbers here, the answer is a number. If there are no numbers here, the answer is a collection of functions. That's the down low on definite versus indefinite integrals. All right, so now let's see the rules. So what's the first rule? The first rule is, well, what is the antiderivative of x to the n? So this is going to be our new power rule. Okay, so to figure out how we're going to do the power rule, we just need to reverse what we did with the power rule for derivatives, right? So let me add a page and we'll visualize that. So for derivatives, x to the n became n times x to the n minus 1. Namely, we did two things. Multiply by the old power, take away 1 from the power. Yes? For antiderivatives, we're going to reverse this process in reverse order. Okay, we're going to do the opposite thing and in the reverse order. Okay, x to the n is going to become x to the n plus 1 all divided by n plus 1. So what did we do? We added 1 to the power, and we divided by the new power. Okay, we divided by the new power. So for example, x squared, if we do its derivative, we multiply by 2 and we make the power 1 less. Yes, so that would give us 2x. But then what would be the antiderivative of x squared? The antiderivative of x squared, we are going to raise the power by 1 and divide by the new power. And that would give us x cubed over 3. Okay, so x cubed over 3 is an antiderivative of x squared. You can always check whether you got the right antiderivative by just taking the derivative of your antiderivative. If you take the derivative of an antiderivative, you should get back your original function, right? So let's do that. If I were to take the derivative of x cubed over 3, well, I would get 3x squared over 3, which the 3's would cancel, and that would give me x squared. So you can double check. Yes, x cubed over 3 is an antiderivative of x squared, because when I do its derivative, I get x squared. Okay. Only I could also add any number that I wanted, right? X cubed over 3 plus 19. If I did its derivative, the 19 just goes right away. Okay? So we can add c to that. So this is the idea behind antiderivatives for the power rule. Is this making sense so far? Let's have some thumbs. Thumbs up if you feel great about reverse power rule, and thumbs down if not so much. Can I have them real high, please? Really high. Okay, cool. That looks pretty good to me. So let's write it down. So the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. Plus c. All right, let's learn some more rules. Why don't we do the antiderivative of e to the kx dx? Well, if I do e to the kx, when I do its derivative, I get k e to the kx. Yes? So to do the derivative of e to the kx, really what you're doing is you are multiplying by k, right? So if we want to do the reverse, we start with e to the kx, and we want to anti-differentiate. Anti-differentiate. Well, instead of multiplying by k, I'm going to do the opposite of that, which is to say I'm going to divide by k. So we would get e to the kx over k. E to the kx over k. So that's what we get when we do the integral, the indefinite integral of e to the kx dx. We get e to the kx divided by k plus c. So I'm adding c every single time because I'm describing a collection of functions. Okay? All of the functions of this form are antiderivatives of this function. All right. So let's quiz the class for the next one. What is going to be the integral of 1 over x dx? What do we think? Well, we want to come up with a function whose derivative is 1 over x. Do we know any functions whose derivative is 1 over x? Yeah, ln of x. The derivative of ln of x is 1 over x. So the antiderivative of 1 over x, of course, has to be ln of x. But we actually pick up an absolute value sign. So I want to just bring your attention. When we're doing an antiderivative here, we always pick up an absolute value sign. Okay. Okay. Should we learn some more rules? Are there even any others? I think that's it, right? I'm trying to think if there's other ones. I feel like I'm missing. Oh, you know what I should look at? Is these. Oh, yeah. I think we got them all. All for today, anyways. Okay, so. What we're going to do now is some group work. So we're going to do integral. I'm just going to rewrite this a little bit. Integral of this thing dx. Integral of this thing dx. Integral of this thing dx. Integral of this thing dt. Okay? So we're going to work on finding some antiderivatives here. I'm going to give you the hint that you should probably try to simplify some of these functions before you try to go and find the antiderivative of them each. Okay? So let's start with this. I'll be walking around to help, and Jacob will also be walking around to help, so just raise your hand if you want a little help. first rule, but also one other rule. This rule. The integral of a number times a function is a number times the integral of a function. Meaning that I can rewrite the integral of 2x to the minus 2x as 2 times the integral of x to the minus 2 subtract x. Yes? And now I can apply the rules because it's in the right form, right? So x to the n, what are we going to do? We're going to add 1 to the power. So if I add 1 to negative 2, I get negative 1. And then what do? I divide by the new power, which is negative 1. So at the end, I get ln absolute value of x minus 2x to the negative 1. So that became a minus because we divided by negative 1. Yeah. Well, we're adding 1 to negative 2. When we add 1 to negative 2, we get negative 1. So we get x to the negative 1 over negative 1. Right? Yeah. So this became x is negative 1 that way divided by negative 1 over negative 1 is plus 1. And the 2 x squared. Right?
Yeah, I didn't see. I was looking at this one. I got like to here.
What's the plus first of all?
Yeah,
but it's not simple, right? We're changing this function into a different number.
Yeah.
So they're not the same, so we shouldn't put a decimal sign here, but yes, exactly. We raise the power by 1, it becomes negative 1. Divide by the true power, which is negative 1. So at the end of the day, we have that the integral, okay, of 1 over x plus 2 over x squared dx is ln absolute value of x plus, becomes plus negative 2 over x.
Yeah, that's where I was. I didn't know where to go from there. Negative 2. Alright.
So negative 2 because it's dividing by negative 1.
Did I do this one correct? Well,
So I think for this one,
because what is that? That just be x squared.
so, right, so the thing is, we have a product here, right? We haven't had anything like a product for anti-derivatives, so what we need to do first here is multiply this out. This is the integral of x squared plus 14x dx. So now, the antiderivative here is going to be 6x cubed over 3. Yeah? And then this one is going to be 14x divided by 1, it becomes what it is to the number. It's to the number 1. So we raise that by 1 and we get 14x squared, and then we have to divide by 2. Okay. How's it going, Colin? Yeah, that looks great. So, technically also you have a plus c here as well, right? But we just write plus c once because we're combining two constants to be another constant.
I could just do a plus C here and then like all this plus C.
Yeah, that'd be maybe a good way of writing it. Either way is fine. Yeah, that looks great. And then so for the first one, yeah, yeah, this is t to the negative 1, but we still have an integral, right?
Yeah.
But, yeah, so the first one, great. This one we can do using the ln, right? Because t to the negative 1 is 1 over t, so it's going to give us an ln. But how about this other one? This looks crazy. But what's the trick we always use is the square roots. We always change it to be a 1/2 power, exactly. So if it's a 1/2 power on bottom and a power 1 on top, then you can combine those by subtracting the powers, right? Same thing you did for the first one. So that'd be t to the positive 1/2 on top, exactly. So that one, we can find its antiderivative using, well, it's not up there anymore, but the power rule, right? Raise the power by 1, divide by the new power, yeah? Is that getting you back on track? Okay. Try to finish it off.
Yeah.
Sorry. This is for the T1, let's see, right? It says 2T. So I'm a little bit confused. When you write equals here, on this side, have you already done the antiderivative? So this is just rewriting? Okay, so if we rewrite, first of all, we need to keep our integral sign. Yeah. So I think t squared, yes, t to the 4 over t squared gets us t squared. I think the other two weren't quite simplified correctly. T over t squared is just t to the negative 1, right? Or 1 over t. And then t over t to the 1/2, right? Is just, we subtract the powers. So the power on top is 1, the power on bottom is 1/2. So that becomes positive 1/2. So I'm not really sure where these 2's are coming from. But this should be a positive 1/2. But then yes, now we have this. And so the first one, t to the minus 1, that's 1 over t. We want to find a function whose derivative is 1 over t. That's ln, yeah? And then for the next two, what are we going to do? Just use the power rule. Raise the power by 1, divide by the power.
So it's C.
So, the only thing I'm a little confused, so yes, well first of all, we want to make sure, okay, from here to here, what did we do? All we did was we multiplied this stuff out, right? So we're still doing an integral, right? So we should rewrite that. And now what do we have to do? We have to find an antiderivative for each of these functions. So I need to find a function whose derivative is 6x squared. So I know the 6 is going to hang out. And I'm going to take this power, raise it by 1, divide by the new power, right? So instead of x cubed over 3 plus 6, the 6 should hang out right here.
Okay, so
Times that
what's the
thing.
C? Where does this come
So the c comes in because the antiderivative of 6x squared, right, is any function of this form, 6x cubed over 3, plus some number, right? Because if we took the derivative of a number, it's just 0. See what I mean? Like if I have x cubed plus 3, and I do its derivative, what do I get? I get 3x squared plus 0, yeah? So whatever that 3 or 5 or 7 or whatever it is, right, is going to become 0. So when we're doing the antiderivative here, the 6x cubed here is then going to have a plus c at the end. So this 14 should be attached here. You see what I mean? So the 14 is going to hang out. Antiderivative of x is x squared over 2 by the power rule. We have a plus c. Even though I did the derivative of antiderivative of 2 functions, you know that if I had a plus c and a plus c, 2 constants, you can combine them together to be 1 constant. Yeah? That makes sense?
So you just leave it like this?
Yeah, exactly. I mean, you could simplify a little bit, and that could be like 2x cubed plus 7x squared, right?
So, this one right here was the one that I was like really wondering about. I don't. Is this like simplified, right? I feel like.
Yeah, it is. And this is exactly correct.
Oh, okay, cool.
Yeah, you did great.
Okay, I was wondering though, what do I do with this? The 2 over x.
Pretty much just whatever.
How do I simplify that, or what do I do to change that?
Well, can you write that as x to a power?
Change it to this.
Dividing by x squared is the same as 2x to the negative 2.
Oh, okay.
See what I mean?
Okay.
And then we can, again, just raise the power by 1, divide by the new
So
power.
it's -1.
Exactly.
I got it.
Yeah.
Thank you.
Oh, so I think what will help you is that x plus 1 over x is the same as x over x plus 1 over x. You see that? Try that and see if it's simple. Good, Dan? You got it right, but we still need a plus c. And also, you need to write an integral sign and a dx here, and then a sign. But yes, you're on the right track. Exactly. Raise the power by 1. It becomes 3. Divide 6x cubed by 3 to get 2x cubed. Same for this one. Raise the power to be squared. Oh, there should be a square here, right? Because you raise the power from 1 to 2 divided by the new power. Yeah, you got it. Oh, so for the first one, the first function, the antiderivative is ln of absolute value of x plus c, and then we add to that the antiderivative of this guy, which we can rewrite 2 over x squared as 2x to the minus 2 and apply the power rule. If we increase the power by 1 from -2, it becomes -1, and we divide by -1, and then of course we add c. The one thing that you notice is we have 2 constants here, right? If I add a constant and I add another constant, well, I'm just going to get another constant. So one way that you can rewrite this would be to say, I'm going to do ln x minus 2 over x, and then just combine those two to just be one constant. Okay? And then I'm going to show one more, which is this one. I can rewrite as 1 over t plus t to the 1/2, because this is t to the 1 over t to the 1/2, and then plus t squared dt gives me ln absolute value of t plus t to the 3/2 divided by 3/2 plus t cubed divided by 3 plus c. So you could rewrite that as ln absolute value of t plus 2t to the 3/2 over 3 plus t cubed over 3 plus c. Okay, so just applying these simplifications so that we can get to a point where we can use either the ln rule or the power rule. Okay, we'll talk more about this next time. Have a good one.